Hello everyone and welcome to my channel. My name is Alessia and today we talk about the implementation and applications of merge sort. Let's take this unordered array and see how merge sort works. Since merge sort is a classic divide and conquer algorithm, it divides the array in half recursively and applies the same sorting algorithm to each of those halves. The sorting algorithm takes the two halves, sorts them, and then returns the ordered merged array. This happens repeatedly until we have the initial array completely sorted. Now that we briefly explained how merge sort works, let's see what data structures we'll need. If we want to sort an array, we'll just need the array itself and a helper array which will be used inside the merge method. We'll start the implementation developing the merge sort function. Let's calculate the array's length and check if it's equal to 1 in order to avoid the useless recursive calls. Now, let's find the middle index of the array and generate two sorted subarrays. After all the recursive calls terminate their job, we can finally merge the two ordered subarrays and obtain our sorted array. Now we'll define the merge function, which will receive the two subarrays and will sort them. Let's start with the definition of the left and right index, and with the definition of an auxiliary array that will store our merged and ordered array. Let's process the subarrays until we fully process one of them. Inside the loop, we compare the current processed element of the left array with the one of the right array, and if the element of the left array has the lowest value, we append it to result and increment the left index. If that's not the case, we append the element of the right array and increment the right index. Once we are out of the while loop, we add the remaining elements of the left or right array to result and then we return it. Let's now rapidly write a test class to make sure that our algorithm works. In the first test, we'll use an unordered array of integers and doubles, while in the second we'll use an unordered array of chars. In both cases, we'll check if merge sort returns the ordered array. Let's now test it. Excellent, it works. Let's now move on to the time and space complexity analysis through big O notation. We'll start with space complexity analysis. As we saw before, to merge two sorted arrays or portions of an array, we need to use a third array to store the result of the merge, to avoid stepping on the component arrays. This leads to a complexity of O of n, with n being the number of elements in the array. Now, let's go through the time complexity analysis. While merging all the elements on each level, we perform linear work, and that's because each of the n elements appears in exactly one subproblem on each level. Since the number of elements in a subproblem gets halved at each level, the number of times we can halve n until we get to 1 is log n. Because the recursion goes log n levels deep and a linear amount of work is done per level, merge sort has a time complexity of O of n log n. Let's now list some of merge sort's applications. First, merge sort is a great algorithm for sorting linked lists. It does not rely on random access to elements, and it's easy to merge two sorted linked lists just by rearranging the pointers, without using any extra space. Second, merge sort is used by databases when the amount of data to sort is too large to fit into the main memory. In that case, they apply merge sort on the data located on a secondary memory, since for merge sort the memory location of data doesn't need to be contiguous. And finally, merge sort is used to solve the inversion count problem, where the degree of sorting of elements is calculated on a list or an array. In case the array is sorted, the degree is 0, and in case of a reverse sorted list, the degree becomes maximum. Okay, that's all for today. Thank you for watching. The complete code is available on GitHub, and if you enjoyed the video and want to support me, like the video and subscribe. Ciao!